Hi, this is an air data computer from Collins. So this is a vintage instrument. This was manufactured in the 70s. You have a date here. This was manufactured in April 1970. This was calibrated last time probably in April 2001. So this is the rear panel. There are two connectors, standard avionic connectors. And on the front of this instrument we have, as usual, pitot-static input pressure here. So we have also 10 annunciators for the altitude digitizer. And we have a selector here, which permits to select between the normal mode and the 4 self-tests here. And we have also these 4 indicators in order to indicate the results of the self-test. So the interesting thing is that I involved the manual also for this unit. So inside this manual we have everything. So we have a small description of this instrument. We have a small description of the internal circuit. Okay, and we have also the schematics and everything, so it can be interesting to see exactly how this thing works. But first we can take a look inside, and after we can have a look on the block schematic in order to understand the overall functioning of this instrument. So let's open this thing first. Okay, so we can see that we have two different sections. So we have on the top of this instrument the electromechanical stuff. So the airspeed measurement is this one, because we have two input pressures on this capsule assembly. So we have the static pressure here, okay, which is connected to this unit and to this one, and the pitot pressure is fed to this tube, and we can see that it is connected to this device here. Okay, and we can see also in that direction it will be better that we have some adjustments. So this for the altitude and here for the airspeed in knot. And on the rear of this instrument we have several boards, electronic boards. So there is also this transformer here. And there is another one here. And here we have several small transformers. I don't know if you can see. I will try to orientate the light. Okay, here. So today we will concentrate to the altitude function. So the altitude function is here. So first we can remove this block. Okay, so this is a nice design. You can separate everything. Okay, so as usual we have several gears. Okay, so let's have a quick view on this thing. So we have here a stack of 3 potentiometers. One has several taps. So we have 2 resolvers here. And as you can see that there is a spring. So these are resolvers which with a clutch, which permits to have a relative measurement. It is something we have already seen in various transducers So this permits to have a measurement relative to a rolled measurement. So we have two of them here, which are identical. So we have two other resolvers here, which are identical to this one, but without the clutch. So the clutch is activated here. So we have the freewheel diode here. It is the same for this one. So because I have already studied the documentation, one resolver permits to have the output of the altitude in one turn. That is to say 0 to 50,000 feet in one turn. And the other one permits to have a fine resolution. So I think that one turn corresponds to 1,000 feet or something like that. And we have also the DC motor here, which permits the servo control loop and the tachometer. So the tachometer permits two things. The tachometer permits to stabilize the servo control loop and permits also to give the rate of change of the altitude. As the angle of the servo control system is proportional to the altitude, the velocity of the shaft is proportional to the rate of change of the altitude. So the output of the tachometer gives directly a measurement of the rate of change of the altitude. So we have here some adjustments. So this is a static adjustment of the altitude. So this permits to have a correction due to the non-linearity of the capsule inside. Okay, so the motor is here, and we can recognize the motor with a very small pinion. So when you have a pinion like that, the device cannot be a resolver. It is impossible. A resolver has always a large ear. The measurement of the resolver is normally one full rotation. So it is impossible to have a measurement using this very small pinion. So let's open the capsule assembly. I think I will place a small mark in order to reassemble in the same position. Okay, so it is always the same technique. If you have understood one time the technique, you will understand every time, because it is always the same with some variant. But this is the classic system. So the capsule here is linked to this shaft here. So there is a shaft. I don't know if you can see. Okay, so this is the peak-off sensor. This part of the sensor is attached to this lever here. The shaft is here, and the orientation of this lever can be changed using the rotation of this. Can see here, you have a kind of screw. I don't know if you see. This screw here is attached to one gear, of course. So this is the feedback of this thing. So the goal is that when there is a change of the altitude, there will be an expansion or a retraction of this capsule. So this will introduce a change on the position of the I bar, and then there will be an imbalance on the output signal of the peak-off sensor here. And the servo control loop will activate the motor in order to retrieve the actual position of the I bar relative to the I bar. So you can see that we have also a counterweight here. So this permits to avoid a change of altitude when there is a change on the position of this unit. Okay, so I will replace the cover, and you can have a look on the block schematic of this thing. Okay, so this is the main specifications of this instrument. So you have the range of altitude, minus 1,000 to 50,000 feet, Mach number 0.2 to 0.95, the airspeed here, the vertical speed up to 600 feet per minute. This is the standard value. And there is also a static source error correction. You will see after what is the purpose of this thing. Okay, so this is the specifications. So we can see that we have effectively two synchros for the altitude. So one synchro gives an altitude of actually from 0 to 130,000 feet for one complete rotation of the synchro, and the second one is the fine synchro, gives a complete rotation for 5,000 feet. And we can see that we have two altitude holds. So these are performed using the two clutched synchros. So we'll see the airspeed module next time, because it is a little bit more complicated. Not the airspeed, but the Mach number. There is also an output for the static air temperature. The static air temperature is not easy to measure, because when you place a temperature sensor outside the aircraft, you will measure the static pressure plus an increase of temperature, which is due to the adiabatic compression of the air, and also the frictions of the air to the fuselage. This realizes actually a rise of the temperature, and the rise of the temperature depends on the Mach number. It is proportional to the Mach number squared. So in order to compute the static outside temperature, you need to measure the total air temperature, and also you need to know the Mach number. And after that you can calculate the static air temperature. Okay, so this is the block diagram of the altitude section. So we have on the left of this page the altitude transducer with the peak-off sensor here. Okay, so you see that the I bar is linked to the capsule, and the E bar here is linked to the shaft here of the servo control. There is obviously a reduction gear between the motor and the shaft. It is not represented on this schematic, but there is here a reduction, of course. So the main loop is here. The motor activates the shaft in order to center the E bar to the I bar. So the error voltage here is fed to the amplifier, which is here. It is a little bit complicated because there are different corrections. So the main circuit is here to the input of the amplifier, which is the altitude servo amplifier. This drives the motor in order to center this E bar. To this shaft we have several things. So we have first the main synchros, which are used for the measurement of the altitude. So these are connected to the rear of this instrument. So this is connected to the indicator in the cockpit, for example. So there is a coarse synchro here, and there is a fine synchro here, 5,000 feet per turn. And there is also the digitizer here. So this is connected to the rear of this instrument. We have also these two clutched synchros with the springs, and we have seen there is springs which permits to center automatically the synchro to the 0 position when the clutch is not engaged. And when the clutch is activated, the synchros are connected mechanically to the shaft, and then the synchro will measure the altitude relative to the hold altitude. So we have also the generator, which is connected to the shaft. The voltage of the generator is amplified, and this gives the altitude rate. And also the generator is fed to the input of the servo amplifier in order to stabilize the loop. So at the input of the amplifier, we have also different things. So we have a scale error. So the scale error permits to correct the nonlinearity of the altitude transducer itself. So there is also a potentiometer which gives an output. So we have actually three different outputs. So one with the potentiometer, one coarse with the synchro here, and one fine also with the synchro. And we have also another potentiometer here, which is linked to the Mach function. So the scale error is a potentiometer with different taps. So this permits to have some specific voltages at a given position of the wiper of the potentiometer, and the potentiometer will interpolate automatically between each specific voltages. So this permits a linearity correction of the altitude. Okay, and the trim pots are connected to this potentiometer here. And the last thing, so the SSEC is actually a correction of the static pressure depending on the Mach number. It is difficult to find a place on the aircraft with a pure static pressure. So there is always a small effect due to the turbulence of the air. So depending on the Mach number, there is also a correction of the static pressure. So this is done by this signal. So this is something interesting. So we can have a look on this correction. Okay, so this is the SSEC correction. It is called the static source error correction. So this is the potentiometer with the different taps, which is linked to the MAC servo control. So depending on the MAC number, the Whipper can change from this position with MAC 0 to MAC 1 here. Okay, and this signal, so this is an AC signal, is fed to the input of the servo control of the altitude. The terminals of the connector are available on the rear of this instrument. So there is a specific transformer in order to set a specific AC voltage at each tap of this potentiometer. And the primaries of this transformer are available on the rear connector here. And there is also this transformer which generates several accurate voltages, and the user can connect each primary here to a specific voltage in order to set a specific correction for a given MAC number. So this is calibrated. This is an example of correction which is applied using these schematics. So depending on the MAC number, so you have a correction in feet, for example 00 and up to 540 feet for MAC 0.925 here. So the correction is 3 millivolts per foot. And there is an example here. So depending on the aircraft, you have a specific correction to be applied. So this depends on the shape of the fuselage and also on the location of the static pressure. So for example, with this aircraft, which is the Gulfstream 2, so depending on the Mach number, you need to apply this correction in feet to the altitude. So this is a correction which is available using the specific voltages which are available for the correction, so it is closed. So there are some examples with some aircraft, so it is different. With some aircraft the correction is positive then negative. For others they are always negative. And for this one, for example, the correction is always positive. So it is possible to change the sign of the correction by you just have to permute the terminals of the primary in order to reverse the phase. If you permute the phase, you will change the sign of the correction. So this is the static source error correction, which permits to correct the input pressure, which is not independent from the speed. So this is a transducer for the altitude. So we can see that we have the worm. So this is called the follow-up shaft. Okay, so the follow-up shaft is linked to this gear here. Okay, and we have the peak-off sensor here. So the excitation coil and the two measurement coils here, which are in series in opposition phase. So when the I bar is centered, we have a 0 volt output. So when the I bar is on the top or on the bottom of this thing, so you have an output signal which will be in phase or out of phase regarding the input phase here. So we can take a look on the electronic side. So in this instrument there are actually 3 servo control loops, one for the altitude, one for the airspeed measurement, and one for the Mach measurement. So this is why we can see that we have 3 identical boards normally, which is this one, and this one. So these are a servo control loop board. So this is just an amplifier in order to drive the motor. I don't know how to remove this thing. Okay, so this is one servo amplifier. So there is no pump here, which is the error amplifier, and one transistor to drive the motor, which is this one probably with the dissipator. So we have 3 boards like this one. Okay, so this is the schematic of the servo amplifier. So there are different versions, so I don't know which one I have. This is dash 2, so this depends on the reference of the op-amp, so I think it is LH101, but I'm not sure, so we can check this thing if we have the last one. Okay, so we can see that we have effectively an op-amp which is LH101, so we have the latest version, dash 2. We have here a modification, so modification 3, so we can find the list of modification probably on this document. We can see that this thing has been repaired. We can see that we have some flux residue. It's not very nice. And this resistor also, it seems that it has been changed. So we can see that we have this error amplifier here. We try to make a small zoom on this thing. So there is a signal input from the peak-off sensor. So we have two right inputs. I don't know if this is so this is the output of the tachometer, but I don't know whether there are two inputs here. So the gain is defined by the ratio of these two resistors for the peak-off sensor. So we have a gain of 51 here. So then the output of the amplifier is fed to this amplifier using this transistor, and this is connected to the motor here. You can see that we have also this transistor which is connected to the peak-off sensor voltage. So this permits to know if the peak-off voltage is 0 or not, because normally when the loop is closed, when the servo control loop is stopped, there is 0 volt at the peak-off sensor. If it is not the case, there will be a voltage across the primary of this transformer. So this voltage appears at the secondary of this transformer. So this transformer is this one. Okay, so you can see that we have a flag input voltage here. Okay, so this voltage permits to activate this relay here. So the flag input voltage here should be large enough in order to activate this SCR, to activate this relay here. If the voltage is not enough, this relay will not be activated. And also the secondary of this transformer is rectified using this diode, and the voltage is inserted in series trigger input of this SCR. So if the input voltage here is too large, there will be a negative voltage at this point here. So the voltage will be on that direction. And in this case, this will not trigger this SCR. So in order to trigger the SCR, the voltage here should be below a given limit. So this is a protection circuit. But the main circuit is only the op-amp and this transistor. So this board permits to have the buffering of the static air temperature and the total airspeed. So we have two buffers with 709 here. So we have another one here. So this is static air temperature. This one is for the measurement of the square root of the absolute value of the total air temperature. Because actually for the measurement of the Mach number and the static temperature, we need to know the square root of the temperature. Okay, so we can see on this block diagram of the airspeed here. So we have on the bottom of this page the block schematics of the measurement of the temperature. The probe actually is a platinum sensor. I think it's 500 ohm sensor. Okay, and there is a resistor here and also a reference voltage here. And due to the specific function, the resistance functions the temperature, actually the voltage at this point is close to the square root of the absolute temperature. So this is a probe which is located in a specific position of the fuselage in order to have stagnation. So this is called the stagnation temperature. That is to say that this probe is located in an area where the airflow is null. And in this case, the sensor will measure the total air temperature, the static temperature, plus the temperature rise due to the frictions and the adiabatic compression of the air. So there is another board here. So this is a very simple schematic. So this schematic is the altitude rate amplifier. The rate here comes from the tachometer. So there is a transformer in order to isolate this thing. There is an amplifier with a gain of 10, and this is fed to another transformer, and the secondary of this transformer is fed to the rate out, which is available on the rear of this instrument. So that's all for this theoretical approach for this air data computer. So next time we will do some tests on this altitude feature, and after that we will continue with the airspeed and the Mach system. Thank you for watching this video. See you next time. Bye.